Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. My purple pen died, and now we had to use a substitute slightly altered color. You'd never notice if I hadn't pointed anything out. We're doing mathematical modeling. Chapter 2 is discrete time models. Section 2.2, we're solving higher order difference equations. This lecture specifically, what we're going to do is solve linear, second order, constant coefficient, non-homogeneous difference equations. Let's get to it. All right. Basically, we're going to phrase the theorem in the last video about the general order K non-homogeneous difference equations, but now it's going to be order 2 instead of order K, and right now we're going to do homogeneous. So order 2 says we're going to have two previous terms, just like the opening card Fibonacci, B would be 1 and C would be 1, and then we can start from there. What we're going to be given is this second order difference equation, which is right now is homogeneous. And we have our initial conditions, x0 is alpha and x1 is beta. The associated characteristic polynomial is going to be a quadratic this time, good. Explicitly, it's r squared minus br minus c. And the general solution is going to be based on the roots of this characteristic polynomial now. If we have two distinct real roots, r1 not equal to r2, then we're going to have that the general solution is C1 R1 to the t plus C2 R2 to the t. This is the most general linearly independent solution. If we have, and again what we do is once we have these initial conditions, we use those to find what C1 and C2 are. We plug those in, I know, just a second. If we have a double real root, she wants to go play with the other kitties. Okay, go play. If we have a double real root, R1 equals R2, which we're just going to call R, then what we're going to get is if we write C1R plus C2R to the t, those won't be linearly independent of each other. Don't worry, we won't get into it. But what's going to happen instead is we're going to multiply one of the coefficients by t, and or what the theorem said is we're going to get a polynomial of, because this is now multiplicity 2, the polynomial standing in front of that is going to be of degree 2 minus 1. Therefore, we should have a linear polynomial as our general solution. And then, again, we find the C1 and C2 using the initial conditions. Finally, and many of you may not have seen complex conjugates or complex variables at all, depending on the course you're taking this for, but I'm going to list it for completeness, and then I'll do possibly one example, but I will keep them off of assignments and exams where if you don't know how to find complex or the polar form of complex numbers, you're not going to be able to explicitly find this solution. But we won't shy away from when there's no real solutions, there's always two complex conjugates for the quadratic equation, and if these are their polar forms, then the general solution is this hot mess. C1 r to the t cos theta t plus C2 r to the t sine theta t, and then again we find the C1 and C2 using the initial conditions. Let's do some examples of this. This is the homogeneous case. Then we'll put f of t here, and it'll make it slightly worse, not better. I like these ones. Let's do it. All right, example 1. We have xt is equal to xt minus 1 plus 2xt minus 2. So from the Fibonacci, all we did was change the 1 to a 2 here. And then we have initial conditions, x0 is 0 and x1 is 1. Basically an on-off starting point, just like the Fibonacci building structure. What are we going to do to solve this? This is homogeneous, first of all, so we don't have to worry about a homogeneous in a particular part. This is just the homogeneous part, is solving this equation. Therefore, what we're going to do is we have the associated characteristic equation is going to be, if you don't remember what we're doing with this, let's do it quickly one more time with this one. We're assuming that xt is r to the t, so that's going to give us r to the t equals r to the t minus 1 plus 2 r to the t minus 2. I move everything to one side to get the characteristic equation. This is going to give me r to the t minus r to the t minus 1 minus 2 r to the t minus 2 equals 0. That is going to be if and only if r to the t minus 2, r squared minus r minus 2 equals 0, or our characteristic polynomial is, you can just memorize if you want, you move everything over first, and it's this one minus this one minus this one, so minus r minus 2. This is our characteristic polynomial. That factors as r minus 2, r plus 1. Factor that however you want. Factoring is difficult in general, especially for degree 3 and higher. But for order 2, we get quadratic, and then we can systematically solve for these roots. What does that tell us? We have case 1, two distinct real roots. R1 is 2 and R2 is -1. What that does for us is immediately from the theorem, it says our general solution is going to be xt is c1 2 to the t plus c2 -1 to the t. This term is just going to alternate back and forth. And then what do we have? We have our initial conditions, so we're going to find specifically what those values are from the initial conditions. We get x0 is 0, which is, now we put 0 into this formula is what we're going to get. And we're going to get c1 plus c2. So this immediately tells us that c2 is equal to -c1. And then from this other initial condition, we get x1 is 1. But putting that into here, we're going to get 2c1 plus, minus c2. And this we can substitute in there, or we get a system of 2 by 2 equations in this one, essentially. But what we're going to get is, this tells us 1 equals 2c1 and then plus c1, because c2 is -c1. So when I put that in there, I get plus c1. And that tells me c1 is 1/3. And then therefore, of course, c2 is -1/3. Therefore, I have my coefficients now that I used my initial conditions to find those coefficients, and I get that the general solution is xt is equal to 1/3 2 to the t plus -1/3 -1 to the t, which I can write cleverly as 1/3 times 2 to the t. This negative I'm going to put into the exponent cleverly, so that will be plus -1 to the t plus 1. This is the explicit closed form general solution to this second order constant coefficient homogeneous difference equation. Coincidentally, I can't help myself, we're not doing induction in this class, but we don't know we're finite creatures, so to actually prove that this formula works for every t, you have to use induction on t. But what this does say is it gives me a nice clever induction problem for students, and I say, do you notice that this was, if you start with this, that we're starting with non-negative or positive numbers, and then we're just adding them, so we're going to get larger and larger positive numbers as we go. So this is an integer every time. But we have a fraction 1/3 here. So what does that say? Prove for every t that 3 divides 2 to the t plus -1 to the t plus 1. That's where we get them from, is from these recurrence relations. So I get a statement that now says, if I erase a little bit over here, prove for t larger than or equal to 1 that 3 divides 2 to the t plus -1 to the t plus 1. And you're like, what? How did you come up? Well, yeah, where are you getting these from? That's where I'm getting these induction statements. Let's do another one. All right, example 2. I've added a 2 into there. I didn't change anything else. I changed that one to a 2 and that one to a 2. That's all we did. Let's restart. We're going to get a much crazier solution this time. What do? This is second order constant coefficient linear homogeneous difference equation with initial conditions 0 and 1 again. What do I do with this? I'm going to find the characteristic equation and then find the roots. If you don't want to make that guess x of t equals r to the t every time, what do? I write it like this: xt minus 2 xt minus 1 minus 2 xt minus 2 equals 0. I bring everything to one side and then I replace these with the r's. This will always be squared 1 r to the 0. So this will be r squared minus 2r minus 2 equals 0. This time we're going to have to get a little bit crazier, and what are we going to do with this? I want to complete the square and solve for r. So b is -2 divided by 1 is -1, squared is 1, so I have to add 1 and subtract 1 from this equation. That's going to give me r squared minus 2r plus 1 minus 1 minus 2 equals 0. This is now the completed square. This is if and only if r minus 1 squared minus 3 equals 0. This is a completed square. Now solve for r. That's why we wanted to complete the square, because now I can take square root plus or minus and we get the two roots. Two distinct real roots, by the way. How did I know? Because the discriminant of this is going to be -2 squared, which is 4 minus 4 times 1 times -2, so plus, so it's positive, so we know that the discriminant of the square root thing is positive, which means that there's going to be two distinct real roots. What are they explicitly? They are equal to r minus 1 squared equals 3, if and only if r minus 1 equals plus or minus the square root of 3, so r is r1, 2, r1 plus or minus root 3, two distinct real roots. What does that say for us? That says that the general solution xt is equal to c1, 1 plus root 3 to the t plus c2, 1 minus root 3 to the t. And then now we have to use our initial conditions to find that c1 and the c2. This is awfully Fibonacci-esque because all we did was change them from 1 to 2s. And then what are we going to get from this? x0 tells me that what? I put 0 in there, and then I use the clever formula that I just got, putting 0 into here. That's going to give me c1, this number to the 0 is 1, plus c2, oh good. This is really nice, by the way, when I give you x0 is 0, or myself, I guess. That says that they're negatives of each other. c2 is negative c1. Therefore, using the next initial condition, x1 is equal to 1, but in this formula, I'm going to get, hot mass, c1 plus 1 plus root 3 plus c2, 1 minus root 3. c2 is negative c1. Then we're going to solve. This says that 1 is equal to, what did I get? This one and this one cancel off, but the roots stay the same, so I'm going to get 2 root 3 c1, which says, c1 is 1 over 2 root 3, and therefore c2 is negative 1 over 2 root 3. Let's put that together and give the general solution to this. This is going to give us the general solution of xt is equal to c1 was 1 over 2 root 3, 1 plus root 3 to the t minus 1 over 2 root 3, 1 minus root 3 to the t. This is the general solution for every t. If you want to know what x 2020 is, you put 2020 in there. I don't know how you're going to calculate that. That's a whole other video, but at least it's one calculation, not 2020 calculations. By the way, this is also amazing. I can't help myself. These are integers. Every time it's just calculating integers, and this hot mess, every time you simplify, it'll be like 27 or some integer, which is amazing. That hot mess is an integer for every t. Let's do more. Solve x to the t equals 6x to the t minus 1 minus 9x to the t minus 2. You can see it, right? Do I have to read it out for you? And then we've got initial conditions, x0 is 4 and x1 is 6. How do we solve this? I use the theorem again. It's homogeneous, constant coefficient, second order linear difference equation. Therefore, what are we going to do with this? I have to find the characteristic polynomial, find the roots, and then phrase this in the general theorem, and then use the initial conditions to find the c1 and the c2. What is that specifically for us? Right here we have xt minus 6 xt minus 1 plus 9 xt minus 2 equals 0. Putting the r's in there, that's going to give me the polynomial p of r, which is r squared minus 6r plus 9 equals 0. What multiplies to give me 9 and adds to give me negative 6, r minus 3 twice. So this is going to be if and only if r minus 3 squared equals 0, or that's the lazy way of writing that. That's why it's a double root. This is r minus 3 times r minus 3. Is that what that 2 means? Equals 0. So r1 equals r2 equals 3. In the general theorem, we put equals r, and you're like, why did you do that? It's like, A, I don't want an index, neither do you, when possible, and it's going to be a fixed number. It's going to be the same root for both indices. What does that tell me? It tells me that my general solution, xt, is going to be c1 plus c2t times 3 to the t. And what do I have to do? I have to use the initial conditions to find c1 and c2. x0 is 4 this time, which is going to give me, I'm putting 0 in there, so be careful. c1 plus c2 times 0 times 3 to the 0 is going to give me, what did we get? c1 alone, which is nice. That tells me that c1 is 4. And the other initial condition, x1 is 6, is going to give me what? c1 plus c2 times 3 to the 1. Or, what does that give me? That gives me 6 6 divided by 3, which is 2, equals C1 plus C2. I already know what C1 is, so that tells me that C2 is 2 minus C1, which is equal to 2 minus 4, which is negative 2. To recap, what that tells me is C1 is 4 and C2 is negative 2. Using that, I can write out the general solution explicitly. What does that give me? From here, and knowing these two values, we get that the general solution is xt is, what did we get? We got 4 minus 2t times 3 to the t for every t. This is the general solution or closed form of this second order recursion relation. Notice that this was the first two examples were two distinct real roots. This is a double real root. I'll let you guess what the next example is going to be. Let's do it. Example 4, for completeness, don't worry about it if you don't know what complex numbers are. Skip forward to the next theorem, which is going to be non-homogeneous. Oh, we'll put a timestamp. By we, I mean someone else. Xt is, all I did was change this one from the example 1 and the example 2. From example 2, I just changed the positive 2 to a negative 2. Same initial conditions. What's going to happen? Now we're going to get complex conjugates when we solve the characteristic polynomial. What do? This is going to be, just for completeness sake, this is second order constant coefficient, a linear or homogeneous difference equation. Go through it every time and then eventually you'll know what all those terms mean. I have xt minus 2 xt minus 1 plus 2 xt minus 2 equals 0. So that gives me my characteristic polynomial, which is going to be r squared minus 2r plus 2 equals 0. Uh-oh. When these are the same sign and larger than that guy, we're in trouble because we're going to get 4 and then minus 8, which is going to give me, oh no, complex conjugates we're going to get. How do I do that? I need to complete the square. When is this 0? If and only if. What do I need? R squared minus 2r plus 1 equals 0. I just take the 2 and stole it this time. Same but different. This is now the completed square. What is that going to give me? That's going to give me r minus 1 squared plus 1 equals 0. And here you might start being like, oh no, can you see it yet? There's no real solutions, and in most other classes we go, okay, you're good, because we don't know what to do. But yes, we do. There's two complex conjugates here. What are they? If and only if r minus 1 squared equals negative 1. And then they're now definitely, you're like, but I have to take the square root. Exactly. That means that r minus 1 is equal to plus or minus the square root of negative 1, which is plus or minus I, we're going to call it. The square root of negative 1. So that means that our roots are 1 and 2 are 1 plus or minus I, two complex conjugates. We should probably draw that. These are two-dimensional numbers. What that means is here's 1, the generator on the real axis, and here is I, the generator on the complex axis. For all intents and purposes, this guy right here is going to be 1 plus I, and its conjugate is going to be 1 minus I, the reflection about the real axis. Don't worry about it. Don't get into it. But that is the Cartesian form of this complex number. I need the polar form of this. So long story short, it's cutting the first quadrant exactly in half. But if you do all of this, this says that my angle is pi over 4 radians, and my radius is going to be the square root of 2. The modulus of this number of I plus 1 is equal to the square root of 1 squared plus 1 squared, which is root 2. It's complex modulus. Don't worry about any of these calculations. This example is just for completeness. What does that tell me? Our 1, 2 in polar form is the square root of 2 times e to the I pi over 4. Plus or minus, where we're going to just use one of these guys. What do I use for that now? No computers, Kitty. Cat's thinking about jumping on all the electronics. Don't do that, we're shooting videos. This is now, long story short, the polar form of the complex numbers. This should be plus or minus, but okay. What are we going to do with that? All I need is one of them. And this tells us that our r is root 2 and our theta is pi over 4. So our general solution is going to be xt is equal to c1 root 2 to the t cos of pi over 4t plus c2 root 2 to the t sine pi over 4t. Now I use the initial conditions. That tells me that x0 is 0, which is equal to, what are we going to get? Cos of 0 is 1, so we're going to get c1 is 0 specifically. That was nice. And then x1 is 1, which is going to be, I'm going to put 1 in there, which is going to be c1 root 2 cos pi over 4 t times 1 plus c2 root 2 to the 1 sine of pi over 4. c1 was 0, so that is gone. And what does that give me? Sine of pi over 4 is, using the unit circle, that's correct. It was rhetorical. Sine of pi over 4 is 1 over root 2, which will nicely cancel. And that tells me C2 is 1. Whew. C2 is 1. And C1 is 0. That tells me that you probably don't want to have, and we're going to pray that I don't give you complex roots in the characteristic equation of a difference equation. But what that tells me is the general solution is xt equals, what was it? C1 was 0, and then C2 was 1, so that is going to be root 2 to the t sine of pi over 4t for every t. And again, that somehow is calculating those numbers, which is starting with integers, but for every one, there's the value. I can't help myself also that root 2 is an exponent 1/2, so to make it even scarier, there's the general solution. 2 to the t over 2 sine pi t over 4. Next, what do we have? We have now a non-homogeneous constant coefficient second order linear difference equation. So this guy specifically is going to be not 0. Then we have initial conditions. We have our associated characteristic polynomial. What is the theorem telling us? Then we have to prove that always the general solution is given by xt is xt homogeneous part solution, and xt is the particular solution. What are those specifically? Xt homogeneous is finding the general solution to the associated when we make this 0, which is the last theorem. That's how we find xt homogeneous. So that's half of the battle. The new half of the battle is, well, I don't know how to find this guy in general actually, but if we have 3 of these special kinds, or more generally, if you have an exponent or a polynomial or an exponent times a polynomial, basically there's one category, this guy. But if you have some nice forms, this tells us how to guess and then use the initial conditions to find these horrible coefficients. What that does for us is it's going to set up n equations and n unknowns, which is going to be horrible. You're going to have to find all these that's the unknowns, undetermined coefficients. You will find them eventually with great effort. So what are the guesses? If you have just an exponent, then we have to be careful. If you have an exponent involved, including 1 to the t, which is just 1, so be very careful with that one. You have to worry about whether that base is a root of our original characteristic polynomial. So there's, yeah, this is where I'm going to get you. If s is not a root, which on at least one, I'm going to give you one where it is a root. But if it's not a root, you just make the guess on determined coefficient a, some number a times that exponent. If it is a root of multiplicity, in this case because it's order 2, it's either going to be a single or double root. If it is a root, then you multiply by t to the m. If it's a single root, you multiply by t. If it's a double root, you multiply by t squared. If we have just a polynomial, there's no exponent involved in those ones, so you don't have to remember about root checking. Good in that case. That's the nice one I give you, or myself next probably. What we're going to have is we just make a guess. This is what you're actually given. It's hard to see in here, but you'll be given actual numbers in there. What you're going to do is guess unknown, general degree, and polynomial, and then find the solutions using the initial conditions. If we have a polynomial times an exponential function, what we have to do now is check, because we have the base again, whether it's a root. If it is not a root, we just multiply a polynomial guess times s to the t. If it is a root, we again have to multiply by t to the m. Depending on the multiplicity, it's either going to be a 1 or 2 in this order 2 scenario. So given these 3 types of non-homogeneous functions, we have a systematic method of undetermined coefficients to find those explicit particular solutions. We can always build the homogeneous solution from the associated homogeneous equation, and then we can build the general equation as the linear combination of the two. What? Let's try that at least once. All right, to finish off, what we're going to do is solve a second order constant coefficient linear non-homogeneous recursion relation with initial conditions x0 is 0 and x1 is 1. What do we do with this? We know immediately from the theorem, hopefully, if we learned anything from that rant of the last few minutes, is that the general solution is xt homogeneous plus xt particular. So we've got two parts to find. Once you find half of the battle and the other half of the battle, then we can put it together and phrase the general solution, which isn't entirely true because once we have that, we still have to use this to find the exact, unique, particular solution. What is that? Homogeneous is the good one. We use the first theorem, we kill the non-homogeneous part, and we solve that, and then we have to cleverly make a guess based on the form of this guy to find the particular solution. Then we use undetermined coefficients. Let's do that. Xt homogeneous. What we have is xt minus 5xt minus 1 plus 6xt minus 2 equals 0. Gives me the characteristic equation r squared minus 5r plus 6 equals 0. I factor that, r minus 2, r minus 3 equals 0. That gives me r1 equals 2 and r2 equals 3. I have two distinct real roots. That means that the general solution to the homogeneous is going to be xt homogeneous is c1 2 to the t plus c2 3 to the t. We don't, when we have a non-homogeneous part, we do not find the C1 and C2 from the initial conditions right now. We wait till the end after we've found our particular solution. Then we'll find those guys. But this is almost what I was saying. This was almost half of the battle once we find the C1 and C2. The second half of the battle is the particular solution. Xt particular is going to be, we have f of t is equal to 3 to the t. Therefore, we guess that our solution is exactly the same form. X to the t particular, our guess is going to be some constant a times 3 to the t. But, careful, s is 3, which is a root of multiplicity 1. So what do I do with that? Since it is a root of multiplicity m equals 1, we multiply also by t. Otherwise it wouldn't work out for us. Therefore, what are we now going to do with that? That tells me that xt minus 1 particular is equal to a 3 to the t minus 1 times t minus 1. Then we're going to put that back, and x to the t minus 2 particular is going to equal a 3 to the t minus 2, t minus 2. We have to put that all back into here and simplify it. So let's move that up and simplify our equation. All right, moving that up, this is what we get when we plug in the t minus 1, and t minus 2 for our guesses. Therefore, we have to put these hot messes back into here. What I'm going to do is bring these two to the other side and then solve for a. What do I get? I get xt, which is a 3 to the t minus 5 times that guy, a 3 to the t minus 1, t minus 1, plus 6 times a 3t to the minus 2, t to the minus 2, equals, the only thing I didn't bring over is 3 to the t. This is the general non-homogeneous equation now. After making this guess, what I have to do is, first of all, what I'm going to do is factor 3 to the t, the lowest power, out of the left-hand side. That gives me, if and only if, 3 to the t minus 2 is at minus 5a times, here I'm going to get 3 squared, or 9. Here I'm going to get times 3, t minus 1, plus 6a, these were all gone, t minus 2 equals 3 to the t. I can now, that's not 0, that's our r guess always, and that's not 0, so I can divide both sides by that. That's going to give me 9at minus 15at plus 15a plus 6at minus 12a equals 3 to the t times 3 to the 2 minus t, which is 3 to the 2, which is 9. Exponent laws. I divided by that guy. What does that give me? Hopefully, if I did this right, 9 and 6 is 15, and negative 15at cancels, and that's going to give me finally, what do I get? That gives me 15 minus 12 is 3a equals 9, or a equals 3. So regardless how we do this, if you make the guess right, the most common mistake is you forget multiplying by the t in the guess because it was a root, and then ever you get 0 equals 0 or a contradiction, and it goes in a circle and you can't figure out what happened. It's because you forgot, made the wrong guess. So that's a check eventually. If when you've done 100 of these and you're getting pretty good at them, when you make a mistake, usually the most common mistake is going to be that you forgot to multiply by t to the power multiplicity of the root in the characteristic equation. What do I do with this a now? That tells me that the general solution was x to the t equals c1, 2 to the t plus c2, 3 to the t plus, what was my a? My a was 3 in my particular solution. So that tells me I'm going to get my xt particular is going to be 3 times 3 to the t times t, or 3 to the t plus 1 t. So this is t times 3 to the t plus 1. Or if you really want, I can write it like this. C1 times 2 to the t plus C2 plus 3t, 3 to the t. If I bring that down, I have 3 to the t in both of those terms, I've noticed. Either way, what do I now have to do? Now I have to use initial conditions to find C1 and C2. Keep this one if you want. From this guy, and using these initial conditions, I see that x0 is 0, and that is going to give me, when I put 0 in there, magically what does that give me? It kills this term, and then this is 1 and this is 1, so that says C1 plus C2. So as usual, that's nice to myself. That tells me that C2 is negative C1. Putting that into here, x1 equals 1, which is going to give me, when I put that in there now, I'm going to get 2c1 plus 3c2 plus, what did we get now? T is 1, so we got 9. I know that c2 is negative c1, so that gives me, this will be negative 3c1. What does that tell me? If I'm doing this correctly, don't skip steps. I'm trying to skip all the steps. That gives me negative c1 equals negative 8. If I move that over, which says c1 is 8, assuming I did that correctly. But up to the constant, we now have the general solution. What is it? Our general solution is, oh, and coincidentally, that means c2 is negative 8. X to the t is equal to c1 is 8, 2 to the t plus negative 8, 3 to the t plus 3t, 3 to the t, or if you want to be really fancy, that's 2 to the 3, so this is 2 to the t plus 3 minus 8 times 1 plus 3t, 3 to the t. This is the general solution to this non-homogeneous second order constant coefficient linear difference equation. Please subscribe right here. I'll see you next time. We're going to do even more. Maybe we'll do some higher order ones. You think they get better? No, they get worse.